All right, so welcome to the second half of chapter 4, which is logarithms. So logarithms is something that is used in finance. It's also used in chemistry. So when you guys get to college, if you take any college chemistry or finance, you'll probably come across some of these logarithms. So we're going to start out today with just basically evaluating the logarithms, and then we'll look at the graphs a little bit. Thankfully, you guys have graphing calculators, so that will be a helpful, useful tool for you when we are doing the graphing portion. Okay, so our objectives here are to evaluate logarithmic functions and then to graph them. So a logarithmic function is the inverse function of the exponential function, and it can be written in the following form, where x equals log base b times y, where the b must be a number greater than 0, and it cannot equal 1. So some type of number in between 0 and 1 or a number greater than 1. So that kind of makes sense because it is the inverse for exponential functions. And when we were just going over those last few sections on exponential functions, we talked about the b being a growth factor or a decay factor. And it was a growth factor when it was greater than 1. And it was a decay factor when it was still positive, but less than 1. So some decimal or a fraction between 0 and 1. But it has to be positive because you can't start from a negative value, right? So because the log is the inverse of that, those same kind of rules apply to the b value. If it's just a 1, nothing's going to happen. It's not going to change. Okay, so logarithm is really an exponent. So basically what happens is if you say log of base b times y equals x, that's really writing b to the x power equals y. It's just the inverse of it. So it's just another, it's like the reverse form of writing that. So same thing here. If I say b to the x power equals y, then that would mean that my exponent is equal to log of this base times y. So it's just a way to kind of go back and forth between the two. So you'll want to definitely use this here as a reference as we're going through some of these problems. So rewriting the equation in exponential form and simplifying. So if I take a look at these, right, basically I want to go from this first form here into this exponential form. The reason we want to do that is because we want to be able to simplify and then later evaluate using this rewriting into the other form. So I don't know if you remember back to an earlier chapter when we went back and forth between fractional exponents and then the different types of roots. It's kind of like that. So sometimes maybe you can't solve a log in your head, but if you convert it into the exponential form, it might be something you can work out in your head without a calculator. So if I take this base here, which is the small little subscript next to your log, and I raise it to the number on the other side of the equal sign, so 2 to the 4th, that should equal 16. And obviously we know 2 to the 4th does equal 16, so that makes sense. So right now we're just rewriting this. We're not solving anything. We're just trying to get used to how we can go from one form to the other. So if we take a look at number 2, we're going to take this little base here, which is a 3. We're going to raise it to the number that is on the other side of the equal sign, and that should equal this larger number here in the spot where the y is. So 3 raised to the negative 3 power, it equals 127. Now that also makes sense because if you remember, if you had like 3 to the negative 3rd, that's really 1 over 3 to the 3rd. And if you worked that out, you would get 1 over 27. So that makes sense that that would work out that way. All right, so let's continue on. So for number 3, our base is this 12. If we raise the 12 to the 0, we will get 1. And that does make sense because any number raised to 0 equals 1. So for number 4, we're going to take our base, which is 98. We're going to raise it to a 2, and that should equal 9604. So if you do that on your calculator, like if you weren't sure and you're like, okay, what is 98 to the 2nd power? it would be 9604. So we're just rewriting these in exponential format because it's something we're more used to and it will make a little bit more sense to us. Okay, number 5. Now this one you might be saying, wait a second, there is no base here. So whenever you have a log with no base, that's implied that it's a 10. So it's kind of like when you have an x without a number in front of it, you know there's really a 1 there. Or you have a variable without an exponent, the exponent is really a 1. Or if you have a square root sign, there's no little 2 in there. You know when you have the radical symbol without a number, it's a 2. So in logs, when you don't see a base number, you know it's really a 10. So for this one, you would take the 10 and raise it to the 2, and that should equal 100, which it does because 10 squared is 100. Now, when you see this ln number, you might say, hey, wait a minute, it looks like something I've seen before because last section we were talking about the natural base e, and on your calculator, when we had to find the e, you'll notice that button ln on your calculator, above it was the e, and that's because that is the inverse of the natural base e. So really what the ln is, it's really a log with a base of e. And for whatever reason, instead of writing log base e, which would make things easier, they change it to an ln. So you have to remember that this is really a log base e. So if I were to rewrite this, my base then is e. I would raise it to the number on the other side of the equal sign, and that should equal this larger number here, 20.086. Now you might be wondering, well, why is this equal sign like squiggly? And that's because it means approximately. Because you remember, the e is actually an irrational number, which means it's a decimal that will go on to infinity. So it doesn't actually equal 3, it's just going to approach it. Okay, so same thing in this case. So if I were to do this here, and I'm going to write the squiggly just because it's not a definitive answer, it's just going to be approximately that number. So for example, if I were to do e, or second ln there, raised to 3, you can see that I get that long decimals, which we're approximating to 20.086. Okay, so that's just how you go back and forth in between the logarithmic form of the function and the exponential form of the function. Okay, so now we're going to use that back and forth to actually solve without using a calculator. Obviously, there's easy ways to do this on a calculator, but we want to understand how we can go back and forth here because we're going to need to use this when we go to solve equations in a later section. So while, yes, you could solve them on a calculator now, if you don't learn how to kind of go back and forth with the two different forms, that's going to hinder you later on. So what I like to do here, since it helps me kind of keep things organized, is I just imagine that all of these are equal to x, and I'm solving for x, basically. Now, if you had a calculator, obviously, you would simply just put in your log base 5, 125 on your calculator. Now, the older calculators, you can't even enter that. It doesn't have a log key where you can enter the base. You have to change a base, which is something I'll show you. The newer calculators do have a log function in there where you can literally just type it in and hit equals, will give you the answer. However, like I said, we do want to be able to do this without the calculator so that it can help us when we're solving later on. So if I want to find out what log base 5, 125 equals, since I cannot do that in my head, I'm going to rewrite it into that exponential form. So I'm going to take my base, which was 5, I'm going to raise it to x, and that should equal 125. Well, now you might know in your head, okay, 5 to what power equals 125? And some of you are going to know that 5 raised to x is the same thing as 5 raised to 3 in this case, because when you raise 5 to 3, you get 125. So this is how we would know that x has to equal 3. And some of you might have said, well, I know 5 to the third power is 125, so x equals 3, and that's fine. Okay, so let's take a look at number 2. So I'm going to rewrite this using the base, and I'm going to raise that to my x I'm trying to solve for, and we know that 2 raised to whatever x is going to equal 16. Now, again, some of you probably already know that x equals 4, which is correct. but I want to show you how to do this by getting the bases the same on both sides, because again, when we get to the equations in 4.6 next week, that's going to be something you have to do. So right here, you want to make these two bases the same. So 2 is a base that we can't really break down, but 16 is really 2 to the 4th power. So the idea here is you want to make both of these numbers have the same base. Once you do that, now the exponents just equal each other. So then x would equal the 4. And that's why that works. Okay, so let's go to number 3. So again, first thing we want to do is we want to rewrite it. So we're going to take the base of 3, raise it to x, equal it to 27. Now you probably already can tell that in your head x is going to be 3, because 3 to the 3rd is 27. So to show you, 3 to the 3rd is another way for me to write that 27. And once your bases are the same, you can just equal those exponents to each other. And that's how we're going to use that to solve some more complicated ones as we get to them. Okay, so now let's take a look at number 4. Now again, there's no base here, which means it's really a 10. So 10 to the x power equals 100. Obviously, to make that 100 really be a base of 10, it's 10 squared, which means x equals 2. All right, so let's try number 5. So again, if there's no base written there, you know it's a 10. So this is really going to be 10 to the x power equals 10,000. Now I want to write 10,000 as a base of 10. So 10 to what power is 10,000? 10 to the 4th power. So now that these both have the same base of 10, I know that x just equals 4. So log base 10 times 10,000 would equal 4. Okay. All right, so number 6, what does log base 816 equal? Well, 8 to the x power equals 16. Now this is where you probably can't figure out x to what power equals 16. Whereas the other 5 problems, you probably could have figured that out in your head. So this is where we now need to change those bases. So 8, there's no way I can change 8 to change 16 to 8 to a power, because 8 to the 1st is 8. 8 to the 2nd, 64. So I'm going to be able to do that. But I can change both of these to be something smaller. So for example, both of them have a base of 2, right? So 2 to the 3rd power is 8. So now this is going to become 2 to the 3rd power to the x. And 16 is 2 to the 4th power. So the idea is to make them both rewrite them so they both have the same base. So now you have 2 to the 3x equals 2 to the 4. We don't need those bases anymore. Once they're the same, you basically can just get rid of them. And now I have 3x equals 4. Divide by 3, so x equals 4/3. So that's one that you may not be able to do in your head. The way 1 through 5 are a little bit easier. You could have probably just figured those out. So that's why you want to understand how to kind of do the thing where you can equal the bases. Okay, so number 7, log of base 64 times 8 equals x. So if I rewrite this, I have 64 to the x power equals 8. So again, I somehow need to make these bases the same. 64 raised to something equals 8. Maybe you know it in your head, maybe you don't. So I want to make these both have the same base. Now I know I can rewrite 64 as 8 squared. So this will be 8 to the 2x. And 8 is really just 8 to the 1st power. So now I don't need those 8s anymore. I'm just going to do 2x equals 1 and solve for x. And I get x equals 1/2. All right, so let's continue on. So number 8, log base 16 times 1/4 equals x. So that would mean 16 to the x power has to equal 1/4. Now, this is a little trickier because you have a fraction. You might be saying I have no idea how to make fraction a different base, right? But you really do, because how do you flip this 1/4? you would just make it be 4 to the negative 1 power, right? So that's the first thing you want to do is get rid of the fraction just by flipping it and making it a negative exponent. Now the 16 I can rewrite as a 4 squared. So now I have the same base. I have 4 to the 2x and 4 to the negative 1. So I no longer need my base of 4. I can just set up the equation 2x equals negative 1, divide by the 2. So x equals negative 1/2. All right, number 9. So again, log base 2 equals 1 over 32. So I'm going to take my 2 and raise it to x, and that's going to equal 1 over 32. Now, immediately when I see a fraction, the first thing I'm going to do is I'm going to flip this and make it 32, and I'm going to raise it to a negative. So now I want to rewrite one or both of those so they have the same base. Well, I can't make 2 any smaller, but 32 could really be written as 2 to the 5th power. And since I have a negative 1 there, it's going to become 2 to the negative 5. Now I no longer need my bases. Since they're the same, I could just get rid of them. So x equals negative 5. Okay, number 10, log base 10, because you don't see one there, you know it's a base 10, equals 1 over 1,000, or sorry, times 1 over 1,000 equals x. So I'm going to take my base of 10, raise it to x, and that should equal 1 over 1,000. First thing I want to do is I want to get rid of that fraction. So I'm going to make it just 1,000, and I'm going to raise it to a negative 1. I want to make my 1,000 have a base of 10. So that would be 10 to the 3rd. But since there's already a negative there, it's going to be 10 to the negative 3. The 10s are the same now, so I can get rid of them. And x simply equals negative 3. Okay, number 11. Log base 8 times 4 equals x. So I'm going to rewrite this as 8 to the x power equals 4. Now, there's no way for me to rewrite the 4 to be an 8 or the 8 to be a 4, so I'm going to have to rewrite both of them as a smaller base. So I know 8 can be rewritten as 2 to the 3rd, and the 4 can be rewritten as 2 squared. Now I have the same base for both of them, so I can get rid of those base 2's. 3x equals 2. Solve for x. X equals 2/3. Okay, number 12. Log base 27 times 1/9 equals x. So 27 to the x power is going to equal 1/9. First thing I want to do is get rid of my fraction, making that 9 to the negative 1. Now I want to try to make these bases the same. So 9 squared is 81, so I can't make 27 a base of 9, but I can make them both bases of a 3. So 3 to the 3rd is 27. 3 squared is 9, so that becomes 3 to the 3x, and over here you get 3 to the negative 2. Now I can get rid of my bases and just solve for that x, and I get x equals negative 2/3. All right, couple more. So number 13, log base 3 times 1 equals x. So I'm going to do 3 to the x equals 1. Now, this is an interesting one because there's no way to make the bases the same here because 3 and 1 are both prime numbers. So there's nothing you can do to break them down. However, this is where you have to just tap into your memory. When you raise something to what number does it always equal 1? And that would be 0. The only way to have 3 raised to a power equal 1 is for x to equal 0. Okay, if you look at number 14, it's going to be the same concept here. 8 to the x equals 1. The only way to have an exponent, something raised to an exponent and equal 1, would be for that exponent to be 0. Unless, of course, it's 1 to the 1st power. All right, and then finally, the last two. we have log base 12 times 12 equals x. So I'm going to do 12 to the x equals 12. Now, obviously, they already have the same base, and this 12 really has an exponent of 1, so that's simply just x equals 1. And then over here on number 16, same idea. When you have a base and this number here the same, basically you're just saying x equals 1. And that's going to be something that we get into on the next page. You're going to learn that when your base and the number that's multiplying to are the same, that they actually cancel out. So let's move on to the next page. Okay, so evaluating the logarithm without using a calculator. So basically, I'm going to write a couple things up at the top here that are important. So if you have log base b, and then this number here is the same, equals x. Oh, my paper got cut off here. That's the same thing as having b raised to the x equal b. So basically what happens here is x just equals 1, okay, in both of those cases. So that's why whenever that happens, that can just cancel out. The same thing happens, oh, this is what I was trying to show when it got cut off. The other situation is when you have b raised to log with the same base like that, and then, you know, whatever that number is, that's just going to equal that x there. Okay, so it says evaluate the logarithm without using a calculator. So do you see how the base here of the exponent and the base of the log are the same? They're just going to cancel out and you're just left with x. Just equals x, whatever that is, whatever number that is. Same thing here. Your base of the exponent is 8. Your base on the log is 8. That all just cancels, and then your answer would just be 10. Same thing goes in the other direction. So here the base on the log is 6. The base of the exponent is 6. So that cancels out, and your answer is just whatever that little exponent there is, which in this case is x. Now on this one, notice you can't just cancel this out because they're two different numbers, but could you rewrite this 81 as like 3 to a power? So it's actually 3 to the 4th power. So now what's going to happen is the log base 3 times 3 will all cancel, and you'll just be left with 4x as your answer. So the last thing I want to mention, which I already mentioned on the last page, is it's called a common logarithm, the log with the base 10. As I mentioned on the last page, when there's a base 10, we just don't write it. So the key on your calculator that just says log, that is a base 10. You do not have a log key for any other base other than 10. Then the ln button is the log with the natural base. Those two are right there for you on the calculator. The other ones are not. So like I said, we don't write log base e, we just write ln, okay? So you just kind of have to kind of remember that. All right, so the last thing we'll do is use the calculator, and then I'm going to stop and we'll pick up this the next day. So evaluating using a calculator, so we're going to round to 3 places. So if I'm going to just put in log 11.5, it doesn't have a base there, which means that it's technically log base 10. So then I'm just going to put my 11.5 in the parentheses. I want to carry out to 3 decimal places, so that would be after the decimal 061. So that would be 1.061. Now, if I want to do the next one, ln of 2/3, okay? So I'm going to go to the ln. Then in here, I'm going to do 2 divided by 3 equals, and then 3 places, so it's negative 0.405. Okay, then the next one, we have log of 25.123. So log of 25.123, then we close that parenthesis. 3 places there would be 1.400. And finally, ln of the square root of 3. So I'm going to type in my ln, then I have my square root of 3, whoops, ln, then my square root of 3. Now, I just have to arrow out and close that parenthesis. If you have one of the older calculators, the radical has its own parenthesis. You'll have to close that first, then close the other one. So be careful with that. And you have 0.549. Okay, so that's pretty much it. As far as finding, we're going to do the inverses and the graphing in the next lesson. I want you to get some practice with just working with these logs first, because it is like a new topic and it can be a little tricky at first. So just on the calculator though, just to kind of look, I'm going to see really quickly if I can find where my logs are on here. Nope, not in there. Not in there. Let's see. And I'm going to have to see if I can remember where it is. I'm sure somebody will probably find that. All right, so I'll have to play around with it. I will show you tomorrow if I can remember where it is on some of these newer calculators. The older ones, you're going to have to change a base anyway when we get there. But that will be it for today. So enjoy the rest of your day. I will finish up this lesson on Thursday, with Friday being a flex day. So it's really just like a makeup day. Anything that you're a little behind in, use that day to catch up, and then you'll have the long weekend, and I will see you after that next week. But we'll finish this one up for tomorrow. Enjoy the rest of your day.